So we've just touched upon Descartes' broader intellectual landscape, weaving together his mathematical work and philosophical ideas. Now let's really zoom in on that mathematical engine he built, his algebra. What exactly made it tick? What was the secret sauce behind its power and its peculiar nature? That's the puzzle we're tackling today. So before Descartes burst onto the scene, how did folks think about math? The Greeks had this neat system. They classified geometry problems based on the tools needed. Straight lines and circles were basic, plain. Conic sections like ellipses and parabolas were more advanced, solid, and even fancier curves were linear. Euclid, the granddaddy, stuck mostly to his two fundamental postulates. Draw a line between any 2 points, draw a circle with any center and radius. Simple, elegant, but honestly pretty limited. You couldn't solve many interesting problems that way. Later guys added a third postulate allowing conic sections, but these were often seen as fancy footwork, purely mathematical curiosities. Aristotle even argued that nature itself preferred simple motions, straight lines for earthly things, circles for celestial bodies. So why bother with complex curves? Well, by the 17th century, reality bit. Cannonballs followed parabolic paths, planets danced in ellipses, and figuring out lenses and mirrors in optics demanded a handle on these curves. The old school methods? Often just clever tricks for specific problems, not systematic ways. And then Descartes rolls in with his geometry. This wasn't just another textbook, it was a game changer. Book 1 tackles problems solvable with just lines and circles. Sounds traditional, right? But hold on, its real purpose, its heart, is something entirely new. It's about using algebra to solve geometry problems, and geometry to solve algebra problems. Think about that. He's basically saying, hey, these two fields aren't separate kingdoms, they're connected by a bridge made of algebraic thinking. Forget just drawing lines. Let's use algebraic operations to manipulate them. This is where the magic begins. How does he pull this off? He starts by showing the direct parallels between arithmetic and geometry. Addition, subtraction, multiplication, division, roots, these aren't just number games anymore. Look at multiplication. He shows you can multiply lengths using only a ruler. Pick a unit length of B, want to multiply by BC. Draw AC, then draw the parallel to AC, boom. B is your product, no calculator needed, just pure geometric construction. And square roots? That needs a bit more muscle, a ruler and compass. Set up a line segment, construct a semicircle over it, drop a perpendicular from the point representing the number you want the root of, and where it hits the circle, that's your square root. Even if it's irrational, the construction works perfectly. The key takeaway: these operations have geometric counterparts. Okay, drawing lines is cool, but Descartes says we don't need to actually draw them. Instead, we label them with letters. Think X, Y, Z. We treat these letters as representing lengths. Here's the genius move. Pretend you've already solved the problem. Figure out how the unknown length relates to the known ones through the geometric setup. Express that relationship in two different ways. For example, maybe the unknown length z equals some known length b, or perhaps z squared equals a times z plus b squared. Each equation represents a different way of calculating the same length. If you have multiple unknowns, you set up multiple equations. Then you combine them algebraically until you isolate one unknown, expressing it as a power, square, cube, etc., equal to some combination of other known quantities. This gives us the algebraic form of the problem. Now, here's where Descartes really flips the script. Back then, an equation with two unknowns, like f of x, y equals 0, was considered a dead end, indeterminate. You couldn't pin down unique values for both x and y. The best you could do was pick a value for x and see what y came out to be. Not really a solution, just a bunch of points. Descartes says, hold on. What if we think of x as the horizontal position, abscissa, and y as the vertical position of a point? Then, for every possible value of x, the equation tells us exactly what y must be. By varying x and finding the corresponding y, we trace out a curve. Suddenly, that seemingly unsolvable equation defines a whole set of points, a complete curve. This transforms the idea of solving such equations from finding a single point to describing an entire geometric locus. Let's see this in action. Descartes tackles Pappus's locus problem, a classic headache from antiquity. Imagine you have several lines on a plane. The task is to find all the points P, such that if you draw lines from P to each given line, making specific angles, the lengths of these drawn lines satisfy a certain condition, like the product of two lengths being proportional to the square of the third. We knew the answer was always a conic section, but nobody had a general method. Descartes applies his algebraic machinery. He picks two lines, AB and BC, as his coordinate axes, though he doesn't draw them perpendicular here for clarity. Let a BC be Y. All other lines and angles are defined relative to these. Now comes the algebraic heavy lifting. Using the given angles and ratios, Descartes expresses the lengths of all those connecting lines, BRCD, BS, CF, BG, BTG, in terms of x, y, and constants derived from the problem setup. For instance, if the ratio chi to br is known, say divided by z, then br equals times x divided by z. He systematically builds expressions for each relevant length. The beauty is, regardless of the complexity, any length related to a fixed point through a given angle can be expressed in the form ax plus by plus c. When you apply the condition of the Pappus problem, like the product of two lengths equals k times the square of the third, you end up with an equation relating x and y. For 3 or 4 lines, this is a quadratic equation. Since quadratics are solvable with ruler and compass, you can find y for any x and plot the curve. Add more lines and the degree of the equation goes up, cubic for 5 or 6 lines, quartic for 7 or 8, etc. It's a systematic, generalizable approach. So, what did Descartes achieve here? He didn't just solve one problem. He solved a major historical puzzle in a way that was elegant, general, and far superior to anything the ancients had. His method wasn't just a trick, it was a fundamental shift. In Book 2, he meticulously showed how second-degree equations correspond to conic sections, giving them a rigorous algebraic foundation. He even touched on higher-degree curves, though he underestimated the complexity involved. His classification of curves, especially his initial dismissal of transcendental curves, sparked debates that continue. Interestingly, his method for drawing tangents to curves was essentially a precursor to differentiation, a concept formalized later by Newton and Leibniz. And in Book 3, he tackled even more complex problems, venturing into territory the Alexandrians barely explored. Most radically, to maintain the generality of his algebraic analysis, he embraced negative and even imaginary roots. Imagine the shock, numbers that weren't even positive integers. This willingness to generalize algebraically, even counterintuitively, was incredibly forward-looking. Now, let's talk about just how original this was. People used to say the Greeks had a geometrical algebra. They solved algebraic problems using geometry because they hit a wall with irrational numbers. Descartes, they claimed, just took this hidden algebra and made it explicit. But is this true? Did the Greeks really have algebraic thinking disguised in geometric terms? Well, many propositions in Euclid look algebraic when translated. Book 2 in particular seems ripe for it. But modern scholarship, notably Jacob Klein, argues otherwise. Klein showed that the conceptual leap required for algebra proper, changing how we think about numbers, didn't happen until Vieta, decades after Descartes. The Pythagoreans, facing irrationals, were trying to avoid them, not solve them with geometry. And often, translating Euclid's propositions into algebra makes them seem almost trivial, losing the geometric insight. So the consensus is shifting. There's little evidence the Greeks operated with genuine algebraic ideas, conscious or unconscious. Descartes wasn't rediscovering something ancient. He was creating something profoundly new. Okay, so if the Greeks didn't have geometrical algebra, how did geometry relate to their math? It played a role, but in a way that actually made arithmetic less abstract, not more. To understand this, we need to look at Aristotle's view of mathematics, especially number. Aristotle believed math objects had matter, but a special kind, noetic matter. Think of it as abstract substance. Why? Because mathematical objects, unlike physical things, don't exist independently or change. They're noetic ideas in the mind. We get them by abstracting from physical numbers and shapes. But properties need something to be instantiated in. Physical properties are in physical stuff. What about abstract properties like number or shape? Aristotle says they need this noetic matter to exist. For geometry, this involves stripping away physical properties, color, texture, and sensible matter, leaving just the idea of extension, length, width, depth. Further abstraction yields planes, lines, points. These substrata, Aristotle argues, are neither physical nor independent. They are this abstract noetic matter. So, what about numbers? How does Aristotle fit them into this noetic matter framework? He does it by linking arithmetic to geometry. Remember, geometry deals with continuous magnitudes, lines you can divide infinitely. Arithmetic, however, deals with discontinuous magnitudes, units, sums of units. Think of a foot length as a unit. You can measure other lengths using this unit. Suddenly, arithmetic becomes metrical geometry. Numbers become lengths, areas, volumes measured in units. This explains why Euclid's number theory, Book 7 to an Ike, is phrased in terms of line lengths. But this view has limitations. It ties numbers to spatial intuition. Multiplication inherently increases dimensionality. Length times length equals area. Area times length equals volume. You can't multiply more than 3 lengths because you run out of spatial dimensions. Numbers are always numbers of something, determinate pluralities, not abstract general magnitudes. This is where Descartes breaks free. Descartes explicitly fights against this spatial view. He uses letters for lengths, sure, but his interpretation is revolutionary. Traditionally, if A is a length, A squared is an area, AB is a rectangle, a cubed is a volume, different dimensions. But Descartes says, nope, within a single algebraic expression representing a length, all terms must have the same dimensionality. Look at his example, 3 times the cube root of a cube minus b cubed plus a b squared. According to him, a cubed, b cubed, and a b squared are all treated as having the same number of dimensions within this context. This is a massive abstraction. It means the operations themselves become more abstract, not constrained by geometry. Unlike the Greeks, moving between arithmetic and geometry for Descartes doesn't limit abstraction, it enhances it. This leads to a crucial difference in goals. The ancients aimed to construct or compute specific determinate results, usually natural numbers. Anything else was impossible. Negative numbers? Forget it. Diophantus dabbled in general magnitudes, but only as steps towards a final numerical answer. Descartes flips this. In Rule the 16th, he contrasts his approach. An arithmetician sees 9 and 12, calculates 9 squared plus 12 squared equals 225, square root of 225 equals 50. Done. But Descartes says, hold on, let's keep it symbolic, use a and b. The hypotenuse is the square root of a squared plus b squared. See how the parts a squared and b squared remain distinct? He insists on preserving these structural distinctions. For Descartes, working with general magnitudes isn't just a convenience, it's the core of mathematics. This allows him to accept numbers that defy intuition, fractions, irrationals, because algebra demands them, and even negative and imaginary roots, because the structure of equations requires them. Intuition takes a backseat to the algebraic structure. This radical embrace of abstraction, driven by algebraic structure, set Descartes on a path, even if unintentionally. Up until the 1830s or 40s, mathematicians expanded the concept of number, fractions, irrationals, negatives, imaginaries, largely following algebraic rules, without much philosophical reflection. Then, things shifted. Mathematicians like Peacock and Boole started thinking about algebra itself as a set of abstract rules applicable to any kind of entity, not just numbers. Hamilton developed quaternions, showing algebraic structures could define entirely new number-like systems. This opened the door for George Boole to create an algebra for logic. He saw that the formal laws of algebra could represent logical operations. Algebra, freed from its numerical shackles, became a tool for analyzing reasoning itself. This is a direct continuation of Descartes' work on abstract algebra, but its development he couldn't have imagined. He focused on algebra as a discovery tool. They used it to analyze the very structure of thought. So Descartes sees algebra's power in its ability to reveal the structure of equations, moving beyond just crunching numbers. He draws an analogy to logic, abstract from specific truths, to study the relationships between them structurally. Leibniz saw this potential clearly, but Descartes himself missed it. He viewed traditional logic, Aristotelian syllogism, as just a fancy way of restating things you already knew. He thought algebra was special because it was a method for discovering new knowledge. This is key. When he criticized ancient math in Rule of Fay, he complained it looked like luck, not skill. He felt they hid their easy discovery method, analysis, behind difficult deductive proofs to impress people. He believed he had rediscovered this true mathematics, this art of discovery. What was this rediscovered art of discovery? Analysis. But Descartes twists the ancient meaning. Pappus talked about theoretical analysis, proving theorems, and problematical analysis, finding unknowns. Descartes grabs onto the latter, using algebra to find solutions. But he throws out the former. He completely rejects the need for synthesis, the traditional deductive proof starting from axioms. Look at his geometry, no boring lists of definitions and postulates. It dives straight into problem-solving techniques. Once you've found the answer using algebra, proving it deductively, redundant. This leads to a radical rejection of deductive inference itself. He thinks deduction doesn't add anything new to knowledge. Leibniz would disagree sharply. He saw deductive structure as essential for organizing and extending knowledge, spotting flaws and gaps. Descartes, focused solely on discovery, missed this crucial aspect. Why did Descartes reject deduction so strongly? Philosophers before him, like the skeptic Sextus Empiricus, raised deep questions. Sextus gave this clever argument: compare if it's day, it's light, it's day, therefore it's light, deductive, with just it's day, it's light, non-deductive. Either the conclusion follows from the premise, making the if statement redundant, or it doesn't, making the if statement false. Deduction seems flawed. Others worried premises just repeat the conclusion, Mill, or that logical truths are tautologies, positivists. But Hobbes's story shows deduction can be transformative. He reads Euclid's famous theorem about the Pythagorean theorem, thinks it's impossible, then follows the deductive proof step by step and is demonstratively convinced. That's epistemic advance. Descartes wrongly assumes deduction never provides this advance. Even if it sometimes doesn't, like if P, then denying its value entirely ignores cases like Hobbes's. His focus on discovery blinded him to deduction's role in establishing knowledge. Okay, Descartes has this incredibly abstract algebra. Great for discovery, maybe even for logic. But then there's the big question. How does this ghostly algebra connect to the real physical world? This is crucial because Descartes wants to build a mathematical physics, a complete description of nature using only mathematics. If his math is purely abstract, how can it describe concrete reality? This is a problem he tackles in his rules for the direction of our native intelligence. Understanding his answer here is key to grasping his entire project, how he thinks abstract thought can grasp the physical world, and what abstraction truly means in his philosophy. Descartes believes all knowledge starts with simple natures, things we intuitively grasp directly, like existence, unity, duration. Our intellect perceives these, but it's influenced by other faculties: imagination, sense perception, memory. In Rule the 14th, he explores the relationship between intellect and imagination, focusing on extension, length, breadth, depth. He argues that even imagining pure extension, without any physical body, relies on a mental image, a bodily representation, even if we think we're imagining it abstractly. Imagination always needs a subject. The intellect, however, can perform a unique operation, abstraction. It can separate the concept of number or extension from the objects being counted or measured. This separation is purely intellectual work. We need to distinguish statements about pure abstraction, intellect's domain, from statements where abstract terms still refer to concrete things, imagination's domain. The intellect's proper objects are these purely abstract entities: thought, doubt, existence, number, extension, things it contemplates within itself. But the intellect can also turn its attention to the ideas present in imagination. And here's the key. Even when dealing with ideas in imagination, the intellect performs abstraction, separating components. But imagination is as necessary. Why? Because the intellect alone deals with indeterminate concepts. Imagination makes them determinate. Think of number. The intellect understands fewness abstractly. Imagination is needed to picture five apples or five line segments. Algebra, in Descartes' view, operates at the level of the intellect's abstract entities. But to connect algebra to the world, imagination must represent these abstract algebraic symbols, like x, y, z, as concrete geometric figures, lines, planes, measures of extension. So, how does this representation work? Descartes singles out spatial extension as the privileged medium. Why? Two reasons. First, algebraic entities can be represented geometrically as lengths, areas, volumes. Second, he argues based on perception that the physical world itself is fundamentally spatially extended. Colors, sounds, smells, these secondary qualities are illusions created by our minds interacting with the world. What's real is just extended substance. Therefore, what our imagination registers as representing the world must also be purely spatial extension. This creates a bridge. So, we get this cognitive schema. At the top, the intellect deals with abstract entities like algebraic variables. Below it, the imagination represents these abstractions using geometric symbols, lines, planes, measures of extension. And at the bottom, the corporeal world is represented in imagination purely as extended magnitude. Notice, pure algebraic thought doesn't directly touch the physical world. It's the imaginative representation of algebra, geometry, that maps onto the imaginative representation of the physical world. This is Descartes' attempt to provide a solid foundation for mathematical physics. It's arguably as central to his philosophy as the famous cogito ergo sum. It's ambitious, complex, and frankly quite breathtaking in its scope. So, wrapping up, Descartes' algebra wasn't just a technical tool, it was a profound act of intellectual liberation. He busted the myth of a hidden geometrical algebra in antiquity. They actually had a very concrete, spatially bound arithmetic. Descartes fused arithmetic and geometry into something far more abstract and powerful. He kicked off the first stage of algebra's evolution, freeing number from space. His rejection of deductive logic stemmed from his view of algebra as a discovery engine, prioritizing epistemic gain. And his ingenious, if controversial, solution to connecting abstract algebra to the physical world was through geometry, using spatial extension as the common ground. It's a testament to his daring vision that laid groundwork not just for math and science, but for philosophy itself. Quite the legacy.